In this chapter, we're going to look at how charged particles move in electric fields and magnetic fields. And the reason for that is to explain how particle accelerators work, and therefore how we found out all the things in the standard model chapter, how we actually discovered those things. So a field in physics is a volume of space, and a force field, i.e. electric force field or magnetic force field, is a volume of space where a force is experienced. So the standard ones we'll look at, we've already looked at gravitational fields, and we'll look at electric and magnetic fields in this. So electric fields are to do with charged objects. Objects with the same charge repel each other, objects with opposite charges attract. And neutral atoms have no overall charge. But you can change that by adding or moving electrons. So the area around a charge will exert a force on any other charge within that. So in this example here, the charge plus Q is setting up an electric field. This is just a way of as visualizing the forces involved. A direction of force on charge in that field depends on the sign of the charge, it's positive or negative. And we pick a convention here, we always define the direction of the electric field as the direction of the force on a positive charge. So whether this is positive or negative, the force arrow here will always point the direction as if this one is a positive charge. So if that charge there was negative, then that arrow will be pointing in towards it. We'll see in a wee second. So field lines are imaginary lines which show the direction in which a small positive charge would move. And there's a symmetry about the pattern as well. So for a positive charge, point charge as we call it here, so basically just a single charge all concentrated at one point, then the lines all point away from here because another positive charge would be repelled. The field lines give an indication of the strength of the force. At point X, when the field lines are closer together, that indicates the field is stronger. At Y, there's more spaced out, it's weaker. If we look at for a negative charge, we get a very similar field. These are called radial fields, a bit like the radius of a circle, or the spokes of a wheel. And all these ones will would point inwards because a positive charge would now experience a force towards that negative charge. Okay, so the field lines always show the direction that a positive charge would experience a force in. Couple of field diagrams you need to know. So those radial ones for positive and negative. And we'll look at what happens when you have pairs of charges involved as well. So if you had two negative charges, then a positive charge would be attracted to them both. So round about kind of to the far side of this one, then it looks a wee bit like the positive charge one that I had a second ago. But there are points in the middle where things would be deflected and they kind of get bent round. And if you were exactly in between these two charges, then there would be a Z point, a 0 point, i.e. you'd be equally attracted in both directions, and so you would experience any net force at that point. Now the most interesting one though, for the purpose we'll see in a wee second, is probably this one. If you had a positive charge on the right hand side and a negative on the left, the field lines, remember, always show the direction of positive charge which experience a force, so it's going to be repelled away from this positive one. So you have the kind of the beginnings of a radial field, but then they get bent round because they get attracted towards this negative one. Now that's particularly useful where if we put lots of positive charges close together up one side and lots of negative charges up the other side, then what we get is something like this. Now that's quite easy to do by having parallel plates. And what you then get is the middle line here, where the force is a nice straight, the field lines are nice and straight. Then that's what you get between the positive and negative here. And so within the plates themselves, you get these parallel lines, and they're all equally spaced. Remember, I talked about spacing of the force lines gives you an indication of the strength. What that means is that the strength of the field is uniform throughout. So you'd have the same force there as you would there and so on. You do get some edge effects, so you get some curving around the edges, but usually we're interested in what's going on within the deep part of the field.